All right, so now we have a table here that shows us many different shapes, and let me zoom in on these shapes because I want to explain something to you before I get started fulfilling the content here. So you see that these shapes have two axes. They have a reference axis, which is the uppercase letters here, or the blue axis, and then they have the red axes that pass through the centroid location. You already know how to find the centroid location, but now I want to show you what the formulas are for the moment of inertias. However, we will of course bring in the centroid location here. So we will first calculate the area for each of these. Then we will define the centroid location in the x direction relative to this corner, to the origin of the coordinate system. Then we will do it for the y direction, again, to this corner. And then we will calculate Ix and Iy. And what I will do here is I will take the formula from the previous page and apply it to this shape, this shape, this shape, and then give you the ultimate answer. And again, you have to understand that there are two axes here shown in each of these pictures. One axis that is the reference axis, and one axis that is the centroid location axis. And with that said, let's get started. Before I get started, let me remind you that Ix was equal to the integral of the area of y squared dA. So that would be our first column there. And I'm just doing this as a reference for myself. And my Iy was equal to the area element x squared dA. Okay, so now let's start to populate this table. For a square, it's very straightforward. You know the area here would be b squared, no surprise there. You know that the centroid location would be b over 2. And same is true for the y direction, b over 2, because it is a rectangle, or actually a square. Therefore, it's identical x bar and y bar. And the same is true for Ix and Iy. And now if I want to focus or complete these equations, like we could derive them and I could prove to you what the numbers will be here, but I will just now go ahead and tell you what to plug in here. So this here would be b to the power of 4 divided by 12. And for now, you just have to believe me. Again, you can derive this. You may ask yourself, where's this 12 coming from? The power of 4 may be very obvious to you because we see here squared and area. So there must be a power of 4 here. But I think this should be enough for now. And because it's a square, of course, we have the same in the other direction. Now let's make it a little bit more interesting and move on to the rectangle. Of course, you know that the area is b times h. No surprise there. You also know that the x centroid location is b over 2, whereas the y centroid location is h over 2. And now maybe you can already guess where we have to go with this formula here. So remember, there's coming from, so y squared dA is really the base times the height, right? So, and here base and height was the same, so b and b, but now I have b and h, and so maybe I need to take one of them out here, so the height or the base. And in fact, I have to take the base out, so it's base times height to the power of 3 divided by 12. And now by necessity, you see that if b and h is the same, then these formulas would be the same, right? Which has to be the case. And again, if you think along, you already know that now I have to flip my logic here, and now it becomes h times b to the power of 3 divided by 12. And I will talk more about this at the end, but this is a formula you definitely need to remember. This is like, if you're an engineer, this is something you want to remember for the rest of your life. You will see this in many different occasions throughout your engineering career, and it's definitely something you will need over and over again. So bh cubed over 12 for a rectangle. Now, how does this apply to a triangle? Let's do the obvious first. The area is 1/2 b times h. The centroid location, we already talked about this in previous classes, is 1/3 b, and be careful here in this case because we're going from here to here, so it's 1/3 and not 2/3. However, if my reference axis would be here, then it would be 2/3. But the way this is given here, it's 1/3. Now same is true for h, 1/3 h. And now the question comes, how do I apply this? And let me point your attention to the triangle, which is really kind of a rectangle that is cut in half, right? And so now if you would just blindly think about that, you may want to guess that it would be bh cubed over 24. But that's not the case, because remember that the height also is squared in here and so on. And so you have to be careful with that. But let me just tell you what you would plug in here. It would be b times h to the cube. That remains the same. And then you have to divide it by 36. And that 36 comes from the triangle being cut in half, or the rectangle being cut in half to a triangle, I should say. But now the next one should not be tricky for you. It is just h times b to the power of 3 divided by 12. And that is another formula you need to remember or memorize. Okay, let's talk about the circles. It becomes a little bit more interesting now. Of course, you know the area for a circle, pi r square. And you also know how to calculate the distance from the centroid axis to the coordinate origin, which is r in this case. So no surprise there. R, the radius, same is true for the other direction. And now I will tell you that often I have to look this up, but this is why I'm giving you the table here, right? So I want you to always be able to look all of these up at once. If these ones I will always remember, but for circles, maybe I should remember them as well. But engineers, you know, they live in tables and they have to look up many tabulated values. So what I'm trying to tell you is, like, don't feel bad if you cannot remember all of them. I just give you all of them here at once. And if I need anything more complicated than the shapes here, I probably would consult a tabulated book or probably use the internet to find my correct numbers. However, here I will now give you the formula. And the formula here would be pi times r to the 4 divided by 4. And it's very important that here the to the power of 4 is there, because once again, square times squared is to the power of 4, and pi is not does not have a dimension, it's just a factor. And so therefore my r needs to be to the power of 4. You probably understand that for the IY, same thing, right? Because it is symmetric about every axis the circle has. So I can just rewrite this. Now for the semicircle, it's a little bit different, but maybe we can get there as well. So first of all, the area, half pi r square. And in the x direction, the distance from the axis to from the coordinate origin to the centroid axis would be also r. And now something that you probably want to memorize for your exam, which is 4r over 3 pi. And again, on your exam, you may look it up, but I usually expect my students everything in this formula to memorize, at least for the test. Right? After that, you can forget it, but you need to know where to find it. So how does this apply to the moment of inertia? Moment of inertia would now be actually, surprise, surprise, half of what we had before. So that means I have to divide this by 8. So pi r to the 4 divided by 8. And just because it's so much fun, let's actually also add a semicircle to it. So let me draw the axis here. Sorry, not a semicircle, a quarter circle. So I'm going to add one more row to your table, which includes now a quarter circle. And that quarter circle has a centroid location as well. And this has therefore also axes. And now I can define my formulas for that last component. So what is my area? My area, of course, is 1 quarter pi r squared. My x location now is very similar to what I have above, 4r divided by 3 pi. And that is the case for both of them now, because it's symmetric about those two axes. And guess what? It is now the quarter circle. The quarter circle is the semicircle divided in two. So therefore now we have pi r to the power of 4 divided by 16. And this again, pi r4 divided by 16. So now you have a table here that is a good reference for you to always find the centroid location and the moment of inertia. And of course the area, but you knew that already. Let me talk about the moment of inertia here, because remember, this is the moment of inertia for simple shapes. So that is fairly important, and therefore I want to make an extra note here on the bottom. So this here is moment of inertia for individual shapes. And that is important to understand, but more important to understand is that this is the moment of inertia about the centroid axis of the individual shape. So that is very important to understand, and I don't know if that already clicked or not, but I want to highlight this for you because it is such an important thing to understand once we move on with this. So what I have given to you here is the moment of inertia for these individual shapes that you see here. But it's not just the moment of inertia about any axis, it's only the moment of inertia about this x-axis and this y-axis, for example. So the red axis here, and that is what you need to understand here. Maybe it makes no sense for you right now why I'm trying to put your attention to this, because you have not seen how we progress with this, but I need you in the future to understand that these are the moment of inertias about the centroid axis of the shape. And in fact, how we gonna term this in the future is actually I bar x prime and I bar y prime. So in future equations, we will refer to these terms that we have derived in these tables here, or in this table. We will actually refer to them as I bar x prime and I bar y prime. So that's what we really have defined here. And that is important for us to understand, because our next step is what we want to now look into shapes that are combined shapes. So let's pretend, for example, our next shape will be an I-beam, and I'm just trying to draw a simple one for you here that is made of effectively 3 rectangles. And each of these rectangles has an individual centroid location, but also the entire shape has a centroid location. So I'm going to put this here as C total. But keep in mind that I can section this into element 1, which has a centroid location. So I'm going to call this here C1. And then I'm going to have another one down here, which has a centroid location there. So that is C2. And then I have one that is actually coinciding with this here. So this is C3. And why am I showing this to you right now? Because if I were now to just sum up my I-axis and my I-Ys, I would completely underestimate the moment of inertia. So if I just say, hey, I'm going to use this formula because they're all rectangles, and I'm just going to take the formula for this rectangle, and for this rectangle, and I sum them up, then I'm completely missing out the fact that this area is far removed from the total centroid. And therefore, I have forgotten that there is stiffness due to gluing these pieces together, if you will. Right? And you can try this at home. You can just take like 2 somewhat elements, let's say like a wooden bar or something like that, and then hold them together or like bend them individually, but then nail them together or glue them together and then bend them again. And you will see it's much more difficult than just the sum of the individual ones. And so that's our next step. So now that we have on this table defined everything that we need to know for individual moment of inertia, so the moment of inertia for this, and for this, we now need to use this information and combine them properly so that we can benefit from the stiffness that the entire system provides. And this is one component in that formula, and I will do that with you on the next page.